Hello, I'm Nikhil Kumar, and welcome to Lab 4 of Physics 2211, Oscillations. So the purpose of this lab is to analyze the motion of a spring mass system with the mass oscillating in two dimensions, x hat and y hat, build a computational predicted model, and compare it to the observed model. Our observed model was made using Tracker, and our predicted model was coded using GlowScript. So what are our main concepts? Well, first we have the energy principle, which states that the system's change in energy is work done by the surroundings plus change in thermal energy exchange with the surroundings. Newton's second law states that an object's acceleration is directly proportional to the net force acting upon it. And we also know that kinetic and potential energy, kinetic energy is the energy of a system in motion, and potential energy is energy stored. So our energy principle states that work done by external forces plus thermal energy. Since our system is just the mass in the spring, we're hoping that the change in energy is conserved or zero. We also need our position and velocity update formulas, and we also need our kinetic and potential energy formulas, which is half mv squared and mgh. These are used in the GlowScript code. We also know that Newton's second law is change of momentum over change of time, and we can use our free body diagram to find that our net force is just spring force plus gravitational force. Our period of our pendulum is 2 pi squared of m over k, and assumptions are that major forces acting on a center of mass is spring force and gravitational force, and the object is only moving in the x and y directions. So what does our experimental procedure look like? Well, first we're going to import the spring video into Tracker, get our data from that, and put it into Excel. Then we're going to create a computational model, and we're going to compare the charts of both the data sets and make final conclusions. Our system is our mass, spring, and earth, and our surroundings are nothing. A preview of our final result is that the total energy remains at zero, proving the energy principle. So the image shows us the setup for Tracker in the first step of the procedure. After the video was uploaded, the calibration was set and the axis was modified due to the pre-lab video, and our initial conditions from the Tracker are initial position and velocity. We also get the object mass and relaxed length from the given video in the pre-lab. So here we calculate our remaining initial conditions. We know we're trying to solve for the value of k, and we can find the period by taking the average period over the waves. So we just calculate the distance between the peak for the y value, and we calculate it as the average is 1.52 seconds. We then plugged it into the formula for period, and we found that k equals 6.872 newtons over meters. So we plug these initial conditions into our computational model, and we plug in all of our initial conditions, including mass, velocity, position, and our coefficients for k, L0, and our formulas for all the energies. In the while loop, we're doing the same thing essentially, except we're also including updates for all these formulas and our energy formulas. And we calculate our delta energy as the sum of delta k plus delta potential energies. So this is how we calculate them. So finally, we get our results, which is basically showing us our predicted and observed waves as position versus time functions in the x and y direction, and they're very similar to each other with some deviation in the troughs of the graphs. And we also have our change in energy versus time. And we can see that our total change in energy is just zero, even though there's all of these different changes in energies. So what are some of the sources of error that lead us to this? Well, first we have human error using Tracker. This becomes in our calibration. This is definitely might have been an issue. And we also have error 2, which is that the system is not isolated from the surroundings. There could be work done from the surroundings that we didn't account for. So our discussion question number 1 for your model system is the energy principle satisfied? Well, yes, the energy principle is satisfied. Since the total change in energy is zero, there are no external forces acting upon the system. This means that the change of energy must be zero, and that means that it's conserved. You can see all these types of energies in the system, but we know that they sum to zero, which is the yellow line. We also see from our second discussion question that how do we calculate the coefficient k in the x and y direction? Well, for this, we do it the same way that we calculated in the y direction. We take our average of period, which in this case we got as 1.646, and we calculate our k from that as 5.86 newtons over meters. And this shows us that different directions changes the value of period, which ultimately affects t. So what's our conclusions? Well, the predicted and observed models have very similar waves, and total energy remains zero. This proves our energy principle.